In the last couple of videos, we explored stereoisomers, molecules that have the same number and type of atom, hence the same molecular formula, but differ in their three-dimensional shape. We learned about diastereomers, which are stereoisomers that aren't mirror images, and we also learned about enantiomers. Those are compounds that are non-superimposable mirror images of one another. They are non-superimposable mirror images because the molecule has at least one chiral center, a carbon atom that has 4 different groups bonded to it. Enantiomers are really perplexing because they can have very strikingly different biological effects. As a result, many drugs are sold not as a mixture of enantiomers, but instead as one specific, highly purified enantiomer. One example of this is Advil, or ibuprofen. This particular molecule exists as a pair of enantiomers. One of those is very effective as an anti-inflammatory painkiller. The other is not effective at all as a painkiller. And we see this time and time again in the field of drug development and drug discovery, that one enantiomer is responsible for the observed biological effect of the compound. So why is that the case that different enantiomers can have very different biological effects? Well, by the end of this video, we will understand why that is the case. Let's take a look at the concept of enantiomers and some current or previous drug molecules that exist as mirror image isomers or enantiomers. Remember that enantiomers are molecules that are related as non-superimposable mirror images of one another. Much like your left versus your right hand, we have molecules that likewise have so-called handedness as well. In the case of the carbon atom here, this is what we would refer to as our so-called chiral carbon here, and likewise over here in the mirror image or the enantiomer of the structure on the left. This is a chiral carbon because it has 4 different groups bonded to it. It has the COOH, carboxylic acid group, it has the hydrogen, it has the amine group, the NH2 group, and it also has a so-called R group. And R is our group here that we could define that as whatever we wanted. We could pretend that's a methyl group here and a methyl group here. So these 2 molecules are identical with the exception of how the atoms are oriented in 3 dimensions, with the atoms relative to the chiral center being mirror images in the structure on the right compared to the structure on the left. This is also the case with structures such as Advil, where Advil exists as 2 enantiomeric molecules, the one on the left here and the one on the right. We should at this point be able to find the chiral center in each of these molecules as we look at the structure of ibuprofen and we apply our knowledge of line angle formulas, scrolling through here and scanning for carbon atoms that have 4 different groups bonded to it. We look here. This carbon only has 3 groups bonded to it because it's got that double bond to the oxygen atom. Hence, it can only have 3 groups total, 1, 2, 3. We come to this carbon atom. This carbon atom that I have my laser pointer on right now is indeed a chiral carbon. I'm going to put a star on it to designate it as that. It's a chiral carbon because as we interpret this line angle formula, we have 3 bonds that are shown explicitly. To fill the octet on that carbon, we need a 4th bond to a hydrogen. Hence, this carbon atom has 4 bonds to it, and those are 4 bonds to different atoms. We have a methyl group, a carboxylic acid, an aromatic group, and a hydrogen as the 4 groups bonded to that carbon. Around the aromatic ring, there can be no chiral carbons there because none of those carbons have 4 different groups bonded to it. They have at most 3 groups bonded because they are carbon-carbon double bonds all the way throughout. Here, at this position, this particular carbon, to fill its octet, would have to have a CH2 group. Therefore, it is not a chiral carbon because it has 2 identical atoms bonded directly there, 2 hydrogens, in other words, of the CH2. Here, at this carbon atom that I have my laser pointer on now, there's 2 identical methyl groups bonded to that carbon, so therefore that carbon cannot be a chiral carbon. A chiral carbon has to have 4 different groups bonded to it. Similarly, at the methyl group here and the methyl group here, at each of these 2 methyl groups that I keep highlighting, Each of those are CH3 groups, and therefore they can never be chiral carbons because they have multiple hydrogen atoms bonded to that particular carbon atom. So in the case of ibuprofen, it has one chiral center, that's that carbon atom right here. If we look at the mirror image of the molecule over here, that mirror image also has one chiral carbon as well, and I put the star on that there, keeping in mind that we imagine there's a mirror right here, where the atom on the left is looking at the mirror and admiring itself as the atom on the right. We have our ball and stick models down here, which you don't need to be too concerned about, but what's really incredible about Advil and a variety of other molecules that exist as enantiomers is the structure on the right is the structure that is effective as an anti-inflammatory and painkiller. The structure on the left is not at all effective as a painkiller. So why is it the case that one of these structures is an anti-inflammatory and the other one is not? We'll get into that in just a little bit. Similarly, the structure of Aleve, or naproxen sodium, is also a molecule that exists as multiple isomers, multiple enantiomers. On the left here versus the right, as we scan the molecule for chiral carbons, we find one chiral carbon here in this structure. That's our carbon right here that has a carboxylic acid group, a methyl group, an aromatic ring, and there would be a hydrogen directly bonded here as well, meaning there's 4 different groups bonded to the same carbon. And that would be the only chiral center in this molecule, because at every other position, we have just 3 groups bonded here, 3 groups bonded to each of these carbon atoms in this bicyclic ring. Bicyclic meaning 2 rings joined together. Oxygen can never be chiral. Chiral by definition is carbons. And out here, a methyl group with 3 hydrogens directly bonded to it can't be chiral, because chiral means it has to have 4 different groups bonded to it. So you have a chiral center there. And in the mirror image, we imagine that the mirror is this object between the 2 of these, is our mirror that I'm just highlighting in blue there. The mirror image of that has a chiral center at that corresponding carbon atom. And so these 2 enantiomers are pretty incredible. And then the one on the left is an anti-inflammatory drug. The one on the right is highly toxic to the liver. So when this compound is synthesized, it's synthesized in a way that creates specifically just the stereoisomer on the left, and that stereoisomer is meticulously purified from any trace amounts of the one on the right, because the one on the right is highly toxic to the liver. So what is seemingly a subtle difference in the structure of these molecules, where they're just non-superposable mirror images of one another, results in a massive difference in the biological effects of the compounds. Thalidomide is a really interesting example of a compound that was marketed in the late 50s and early 60s as a treatment for morning sickness and a sleep aid for pregnant women. And in the case of these structures, one of the enantiomers was the treatment for morning sickness and a sleep aid. The other was a teratogen, a substance that causes birth defects, such as those seen here on the right side of your slide. And so thalidomide was taken off the market. Interestingly, it has since been reintroduced into the market more recently as a cancer drug, but of course, a cancer drug that is carefully kept away from expectant mothers. So in the case of thalidomide, if we look for the chiral center here that allows it to have an enantiomer, non-superposable mirror image, that actually already has a star on it for us. That's right here at this carbon atom here versus here, with imagining a mirror between these 2 substances, and they are mirror images of one another. At this carbon atom, we have 4 different groups bonded to it, because we have a nitrogen, we have our carbonyl carbon here, and we have a CH2 here, and we have a hydrogen that is not shown there to make the full tetrahedron at this carbon, meaning that this is a chiral carbon. All the other carbon atoms, CH2, CH2, carbon-oxygen double bond, carbon-oxygen double bond, carbon-carbon double bonds, and carbon-oxygen double bonds over here cannot be chiral centers, because there's no way those can have 4 different groups bonded to it. If they have a CO double bond or a CC double bond, that means there's no way there's 4 groups bonded to that. So these represent enantiomers of one another that have very different biological impacts. So why is it the case in each of these molecules and a plethora of others that one enantiomer has a very promising medical effect and the other perhaps has no effect at all in the case of ibuprofen, or in the extreme example of thalidomide is highly toxic? It has to do with how drugs act. Drugs function generally by binding to protein targets. proteins have a unique three-dimensional shape, as we will learn in a later unit. And in order for a drug molecule to impact a protein and hence impact a disease, that protein's structure in 3 dimensions has to be perfectly complementary to the 3-dimensional shape of the drug molecule, so the drug molecule can bind to that protein molecule. And a way of showing this as a schematic is if we imagine that what's shown in this mustard color here and here are the so-called receptor sites on a protein, that is where the drug molecule is going to bind. And we imagine that the protein has a triangular shape here in 3-dimensional space, a square shape here, and a circle shape here. In order for a drug to function, it needs to bind to those 3 sites in 3-dimensional space perfectly. It needs to be perfectly complementary, in other words. And so if we look at 2 structures related to one another as enantiomers, the structure on the left versus the structure on the right, those are related as enantiomers because they are mirror images of one another. If we imagine there was a mirror here, we would see that the thumbs are pointed toward each other there in purple, or whatever you want to call that part of the molecule, and that this is a chiral center here in black as our carbon atom. We would observe that if each of those 2 molecules that are related as enantiomers attempted to bind to the receptor site on the protein, the structure on the left would be perfectly complementary because the triangular part of that molecule lines up with the triangle on the protein, the square or box part here lines up with that, and the sphere in green lines up with the spherical shape on the protein binding site. And so it fits perfectly, therefore leading to a biological response, such as the protein is inhibited or the protein is activated, leading to a reduction in pain or whatever the intended biological impact is of that drug. On the other hand, the enantiomer would lack the ability to bind to this particular receptor site on the protein, and hence it would not have that biological effect. Why do some enantiomers then have very, very different side effects, such as in the case of thalidomide, one being a morning sickness treatment, the other being a agent that causes birth defects, is because this molecule on the right that doesn't bind to this particular protein might bind to some other protein in the body, and that could have a highly toxic effect. And so different enantiomers have very different biological effects because they are 3-dimensional shapes that are going to interact differently with different 3-dimensional shapes, meaning different biomolecules such as proteins. And now that we've looked at why these have different biological effects, in the next segment, we will describe how we can mention in words what the configuration or the 3-dimensional shape of these different enantiomers are, so that we can recognize in words when we spell out the name of a compound whether that particular compound is the enantiomer on the left or the enantiomer on the right. And it's very important to be able to do that because we need to be able to describe in words whether a structure is going to be able to act as a biological treatment for a particular disease. Also, as we will learn later in this chapter, sugar molecules exist as multiple stereoisomers. We need to be able to describe in words what particular sugar molecule we are dealing with. This is also going to be true as we get into biomolecules in later chapters, such as the building blocks of proteins exist as multiple stereoisomers or exist as enantiomers. And so we need to become proficient at using words to describe how we would go about discussing the different enantiomers that are possible for a molecule.